I'd like to also review trying to find review the derivatives of exponential functions. Um, and let's say we have some exponential function y equals some base of x. We don't really know what the base is. It doesn't really matter. It's a real number though. And we'd like to figure out what is the derivative of this. Well, if we don't know any better, and if you don't have your rules from AP Calculus still memorized or sharp, then we can at least try to come up with what they would be because we know how to find the derivative from first principles, meaning we can use the limit definition to find one. So recall, if f of x is some base to the x power, then by definition, the derivative of this function should be b to the x plus h minus b to the x over h. And this is in limit as h tends to 0. Or, if with a little rearranging, note that exponent rules say that this is the same as the limit as h tends to 0 of b to the x times b to the h minus b to the x over h, which means you could factor a b to the x out, which means this is the limit as h tends to 0 of b to the x, b to the x, times b to the h minus 1 over h. Which, since this b to the x term doesn't have any h's in it, you can pull that out of the limit. You get something like this. Note that if you thought of this function, the derivative of this function at 0, that would be the lim as h tends to 0 of b to the 0 plus h minus b to the 0 over h, which is the limit as h tends to 0 of b to the h minus 1 over h. And that's to say that these two things are the same. So put that together, what do we have? So we find that the derivative of this function, the derivative of this function of some base b, is equal to this base to the x power times its derivative at 0, which is nice. That's kind of handy. So it tells us that these functions are really just the original function times some value of its derivative at the point x equals 0. So whatever the value is derivative at x equals 0 happens to be, that'll be the constant we multiply to our function, and we'll have an understanding of what the derivative happens to be. But this is kind of curious to me, in that you can make this a really special function if you could find some base such that the following is true. You'd have a really cool function. If its derivative at 0 was exactly 1, then you would know a function with this really sweet property. With the property that the function is just equal to its derivative. For you, if you remember a little bit from Calc 1, you probably know where this is headed, but this is, I think, a kind of a nifty, kind of a cool thing to do. At least cool mathematically. So if we could find one, if we could figure out what that would be, we can do this. So we can do this. Let's find one. Let's find that base. So what does that mean? We need the derivative of this crazy function to be 1, which means we need the limit as h tends to 0 of this base to the h power minus 1 over h is 1. We need this statement to be true. So I'm going to start by doing a little bit of algebra. I'm going to get b to the h by itself. So I think I'm going to look at this equation here. I'm going to multiply both sides by h and then add 1 to both sides. So I think we can hopefully can agree that now I should have something that looks like this. The limit as h tends to 0 of b to the h should be the same as the limit as h tends to 0 of multiply by h and add 1 of an expression like this. How can I manipulate this a little bit? I'd like to get b by itself. So if you remember from pre-calc and algebra 2, how do I do that? I think I'd like to undo this exponent by using a rational exponent. So maybe I'm going to raise both sides of this equation to the 1 over h power. So I'll multiply these two exponents again. This would be just the 1 power. So now I'm looking at the limit as h tends to 0 of just b, which is, by the way, just the base. And this would be the limit as h tends to 0 of h plus 1 to the 1 over h power. This limit is a little awkward. It's not exactly clear what this should evaluate to be. However, with a change of variables, this will get us into a form that, if you didn't already know what it is an important feature and something to know from calculus. I'm going to make the following change of variables. I'm going to let n equal 1 over h. So what does that tell me? What does that do? So immediately I can just take out this 1 over h and put an n in its place. Can put an n in its place. Still have this 1. Well, if n is 1 over h, then I think h is 1 over n. And the only question is, well, if h was heading to 0, what does n tend towards? Well, I think n should be tending to like 1 over 0. And I think it's pretty reasonable to claim that if h is tending to 0, then n is blowing up. If h is getting really tiny, then n is getting really big. So I think the equivalent statement of h going to 0 with this change of variables is that n is tending to infinity. So the base of this exponent, of this exponential function, should be whatever this number evaluates to. And if you don't know what this evaluates to, this is here's a point of culture, and it's a pretty important fact. This is the definition of one of the most important numbers in all of mathematics, and one of the numbers that crops up almost as frequently, if not more frequently, than pi, and it's Euler's number e. This is the definition of Euler's number. E. Which tells us that the result of maybe our favorite thing to find the derivatives of in AP Calculus is that the derivative is that if the function f of x is e to the x, e to the x is equal to its derivative. We're going to investigate a couple more derivative rules that you learned in AP Calculus that are directly related to implicit differentiation. The first is to find the derivative of the natural logarithm. And I'm going to state the formula in just a second. But before we do that, I'd like to, before I just state it, I'd like to derive it. We'll figure out what it comes from. It's really quick. It's a classic use of implicit differentiation, and I think it's a good eye-opener to see where some of these formulas come from. So let's let y equals the natural log of x. And then we're going to try to figure out what is dy dx in this case without knowing the derivative of natural log ahead of time. What I do know is that the natural log has an inverse function, and I could rewrite this as x is equal to e to the y. Note that these should be equivalent statements. The reason I do this is because I know how to find the derivative of e to the x fairly easy. So let's find the derivative of both sides. This tells me that 1 is equal to e to the y times dy dx. What's cool, or what's nice, is that we know what e to the y is equal to. This is just x. So this is really saying 1 equals x times dy dx, or better yet, dy dx is equal to 1 over x. So note the derivative with respect to x, of the natural log, is just 1 over x. Again, nothing new, nothing shocking from AP Calc. Maybe something you just were told and went with, but this is where it comes from, and this is a pretty common thing that you'll be asked to derive on an IB exam for sure. Let's look at a few more derivative rules that you were just given in AP Calc. Note that almost all of these derivative rules are in the IB formula pack, so you'll have access to those during the assessments in this course. And those of you that are taking the IB exam, you'll have access to those during your tests. So they're not things that you necessarily need to have memorized, but having them memorized will lead to a lot less frustration in the middle of tests in this course than in the eventual exam. I'm going to state these rules first, and then we'll derive one of them. We'll derive figure out how to come up with this derivative rule for arcsine. If you recall from AP Calc, the derivative of arcsine, or inverse sine, is positive 1 over the square root of 1 minus x squared. Cosine, derivative of arc cosine, is basically the same, just it's negative. And the derivative of arctangent is 1 over 1 plus x squared. Again, these are all formulas from AP Calc, and these are in your formula pack. Although I do want to take the time to show and derive where at least one of these comes from. This is again a classic implicit differentiation example that comes up often in exams or in the middle of questions, or just frankly if you forget what the derivative is and you don't have your formula pack or you panic, this is a quick way to try to come up with it, and this is a technique we use to solve other problems as well. So we're going to find the derivative of arcsine, and in much the same way as we did for natural log, we'll let y equal the arc sine of x, which means that x is equal to the sine of y. And again, if you want to get real precise, there's some restricted domain. You have to restrict the domain to make this a function, and blah blah blah. There's more technical details to it. We're gonna ignore those for now, but if you really want to make this proof very rigorous, you would go into that, but it's not necessary to understand what's going on. So again, just like the natural log, we'll take the derivative of both sides. Sine y, which means 1 is equal to cosine of y times dy dx. And moreover, this tells us, note that this tells us that dy dx is just 1 over the cosine of y. That would be nice, but we know what sine of y is, we don't know what cosine y is. So it would be helpful to try to figure out what the heck that is. It turns out we can, because we know, and you should know, some trigonometric identities. In particular, the most famous of them, the Pythagorean identities. Sine squared plus cosine squared equals 1. So solving for cosine, we find that cosine of y is equal to square root of 1 minus sine squared of y, which is another way to say square root of 1 minus sine of y squared. So this tells me that dy dx is equal to 1 over the square root of 1 minus sine of y squared. And what do you know? Sine of y is equal to x. Thus, this is 1 over square root of 1 minus x squared. The proof for arc cosine works very similar, and same with tangent as well. If you know each of these rules, we can work to figure out what is the derivative of arctangent as well.